Hi, I'm Baptiste Genest, I'm a French PhD student, and today I'm going to talk to you about our work and certainty-aware geometry processing on Gaussian process implicit surfaces. And this is joint work with David Coeurjolly. So, the core of this work is fundamentally about the question, how do you do geometry processing when your input looks like this? Okay, so like there are lots of holes, there is noise, etc. So like we're not even sure what's the actual geometry we're supposed to do geometry processing on. Of course, there is kind of a natural way to handle this case, is to first reconstruct a clean surface, and then to do geometry processing on this particular surface. And so this is a perfectly fine answer 99% of the time, but there is kind of a blind spot, right? Why this one in particular? I mean, if I show you all those variations of the shape, they are all coherent with our input, and yet the result is completely agnostic of this ambiguity, right? And so that's precisely our goal. First, how do we define a notion of probability distribution of shapes that is coherent with a given input? And then how do we define a notion of computation over such distribution of shapes? And so, for instance, when we are going to do geodesic distance and shortest path computation, we are going to be able to provide natural answers to, for instance, the question, should we consider that there is a hole, like, should I consider that my geometry, there's a hole in my geometry, or should I can trust enough my data and to say that the reconstructed surface is right about ignoring the hole? Okay, so that's precisely what we want to do. All right, so first, how do we encode a probability distribution over the shape of spaces that are coherent with an input? We are going to do that with Gaussian process implicit surfaces. Okay, so previous work mostly define GPIS through Gaussian process regression. You don't need to know what it is, just know that it's a very elegant solution, but it's quite an expensive one. Okay, and so we wanted something that was super simple, very easy to evaluate, and that would be easily parameterizable. Okay, and so that's why we started from you can start from any closed form pointwise implicit surface reconstruction scheme. Okay, so like here, for example, you can imagine the winding number. So like at any point in space, I have my given set of position and weighted normals. Okay, so like that's what I consider to be my input, and such reconstruction scheme will give you at any point in space a scalar value. Okay, and if you consider this entire scalar field, when you consider one particular is a surface, for example here the 0 is a surface, you get you get your reconstructed shape. All right. But so this we want to be able to incorporate our uncertainty about our shape. So how do we do that? Well, we are going to first assume Gaussian noise on our input. So like Gaussian noise on the position and Gaussian noise on the weighted normals. Okay. But then the output that we obtain is not Gaussian anymore, because Gaussians are only stable by affine maps, and this is not because like our reconstruction scheme is not going to be affine with respect to our input in most cases. And so to obtain an affine map, we simply do a simple first order Taylor expansion with respect to those input parameters. Okay, so like what matters here is that now at any point in space I can query this field, and since it ends up being a linear combination of Gaussians, that is the base, like the field that I had before, which is our mean field, plus all those additional terms that depend on the noise, which are sensitivity measurements. And then since they are with respect to this Gaussian noise, at any point in space I end up with a Gaussian distribution. Okay, so that's all there is to it. And the important thing to notice is that if I consider the isosurface of a standard scalar field, I get one surface, but if I consider an isosurface of a random scalar field, then we get random surfaces. Okay, and so that's precisely how we're going to encode distribution of shapes that are that we depend on a given input in our modeling, or like the way we conceive the noise that we can assume on our data. So that sounds nice, but what can you even do? Like, how do you even do geometry on that kind of implicit stochastic representation? For instance, there is this very famous fact about implicit geometry is that when you are on the isosurface, if you take the gradient of the scalar field, it is collinear with the normal of the isosurface at any point x. Okay, so how can we recover this fact in this setting? Well, one thing that you can always do, no matter the GPIS model, okay, so before I presented our GPIS model, which is very simple, but what I'm going to present from now on is completely agnostic of the kind of GPIS that you're using, okay? So, one thing that you can always do is to query the joint distribution at any point x of the value of the scalar field, of this random scalar field, and the value of the gradient of this random scalar field, okay, so it's a Gaussian process. And the thing that is very nice is that this joint distribution of those two quantities, okay, since there are two quantities are obviously like correlated, well, they in fact follow a Gaussian distribution itself. Like this joint distribution is also a Gaussian distribution. And so when we had like one coordinate for the value of the field, and for example in R3 we have three coordinates for the value of the gradient, which means that this joint distribution is a four-dimensional Gaussian vector, right? And so what can we do with that? Well, one thing that we can ask, and what we'll always do with Gaussian variables, is to ask for the conditioning. Okay, so like the conditioning will tell you, for example here, what's the distribution of the gradient under the hypothesis that the value of f of my field at x is 0. Okay, so like that's the same as stating what's the distribution of the gradient under the hypothesis that the surface runs through x. Okay, and then, since we know that we are under the hypothesis that the surface runs through x, that means that the gradient is indeed the normal of the isosurface. Okay, and so this means that we get the distribution, the Gaussian distribution over the normal vectors at any point in space under this hypothesis that my surface runs through x. Okay, and so here, just so you know, this is simple Gaussian algebra, but it's very simple math. Okay, so with GPIS you can get the Gaussian distribution of normal vectors and tangent planes with simple math. Okay, so that's very nice. Okay, so now how do we define a notion of computation on GPIS? Well, our goal is to define probabilistic analogs of standard differential operators. Okay, so like the Laplacian, the gradient, and the divergence. We are going to go through a very standard path in differential geometry, which to start from integral geometric energies. Okay, so for example, the Dirichlet energy. The Dirichlet energy, in our implicit setting, you can consider an ambient scalar field, and then the Dirichlet energy will simply be the squared norm of the tangential variation over this function along our shape. Okay, but what is important is that it's an integral that depends on both our shape and our function. And then, for example, the usual way to define the kac-rice the Laplace-Beltrami operator is to consider the functional gradient of this Dirichlet energy. Okay, and so the standard Laplace-Beltrami operator can be defined through the functional gradient of the standard Dirichlet energy. All right, and so that's precisely what we want to do here on GPIS. But of course, there is kind of a problem. Is that since we are considering integrals over random surfaces, that means that integrals themselves become random variables. Okay, so of course that's a problem. And of course the first quantity to consider is the expected value. Okay, what's the expected value of an integral over a random distribution of shapes? And so that's precisely what we are going to do. But first, to recall the setting, I have my volumetric domain omega, and I have my distribution of shapes, and I consider an ambient scalar field f. And our core contribution is to show that the kac-rice formula that exists in pure math is perfect for the job. Okay, because the kac-rice formula will simply tell you you can go from this expected value of this integral over your distribution of shapes and simply go into a simple volumetric integration. Okay, that will only depend on like closed form in some sense parameters that will only depend on the distribution of the field itself. Okay, so it's a super useful tool because it allows us to go from random surfaces to a simple volumetric integration that is fully deterministic. Okay, so that's extremely powerful. And for example, as you can see, this is integrated with respect to the probability density function of the Gaussian field. Okay, so like it's essentially weighting the integral with respect to both the probability to find the shape at some point and the norm of the gradient. Okay, the norm of the gradient of the field is something that comes from the Coeurjolly formula, and essentially it's the right way to give mass to an implicit field. Okay, but truly you don't need to understand this formula. All you need to know is that it will allow us to go from random surfaces that we don't want to generate, and so that we never have to generate, to purely ambient space integration and computation that will only depend on closed form expression that involve the distribution of the scalar field itself. Okay, so that's very powerful. All right. The simplest example is what happens if you integrate the constant function over GPIS. Then what you are going to see is that you are in fact integrating with respect to this measure that we call mu. Okay, so mu is simply the probability that the Gaussian process is equal to your isosurface at in point x times this co-area weight that we just discussed. Okay, but you don't need to understand the formula, just know that it appears to be a very fundamental object for GPIS because it corresponds to the uniform sampling density over your shape. It's also, if you consider its total mass, so like the integral over mu over the entire domain will be equal to the expected area of your shape. Okay, so that's why we're going to interpret it as an actual volume form. And there is an additional property that is very nice, and that is essentially stating if I apply a function that might be non-linear to my Gaussian field, but like if it only preserves the level set that I'm considering, even if the output is not going to be a Gaussian process anymore, the thing that is very interesting is that mu will be invariant with respect to this transformation. Okay, so it means that all the stuff that we are describing is fundamentally linked to the distribution of the isosurfaces themselves and not to the Gaussian process field ambient representation that we have. Okay, so like it's a sanity check that tells us we truly are doing computation with respect to a distribution of surfaces and not from scalar fields. Okay, so that's very interesting. So that's for mu. And then we want to, so like that was the simplest setting, but now the energy that interests us, the Dirichlet energy that we define once again as this integral. Okay, so you can apply the kac-rice formula here, okay, but I won't dive into the math because it's not necessary. Please check the paper if you want to understand it more. But from the point of view of intuition, it's very, very simple. Okay, so the kac-rice formula simply tells you to get the expected Dirichlet energy over GPIS over your domain. What you can do is at any point in space X, you can first compute the conditioning of your, to work under the hypothesis that the surface runs through X. Then you take your ambient scalar field, you compute its Euclidean gradient, and then you project it along the current tangent plane. Okay, and the kac-rice formula simply tells you to get the expected Dirichlet energy, you can simply take the average of the squared norm of this projected gradient of our field. Okay, so really it's a very intuitive stuff. It will truly measure how well aligned are the variations of your shape, of your function, with the variations of the tangent planes, essentially. Okay, so it's a very intuitive process. And then you can do that for all the point x in your domain. And but what is important here is that just as the standard Laplacian was defined as the functional gradient of the standard Dirichlet energy, we define the kac-rice Laplace-Beltrami operator as the functional gradient of this expected Dirichlet energy over GPIS. Okay, what is fundamental here is that it boils down to a simple volumetric anisotropic diffusion operator in the ambient space. Okay, and what is very nice is that we found that it's in fact a generalization of the Laplacian and implicit surfaces that has been defined 20 years ago. Okay, so like when you have very low uncertainty, our operator will converge weakly to these standard Laplacian on implicit surfaces, but as soon as uncertainty is not zero, which is always the case here, we obtain a regularized version of the Laplacian in the sense that this operator that we define is strictly elliptic. Okay, so it means that we know that solution to PDEs will exist, that they are smooth, etc., etc. So like this tells us that having this stochastic point of view makes operators behave better than in the standard setting. Okay, so that's a very reassuring view because it's a quite common one. Okay. And so the fundamental object in this operator is this tensor field T, okay? And so T is in fact simply the expected, like the average projector tensor over any point at any point in space. Okay, so like mu will tell you what's the probability to find the shape at any point in space, and T will tell you if the shape runs here, here is the distribution of the tangent plane. Okay, so like those two objects are enough for what we're doing to define computations. Okay. And so from those objects, we can define first-order differential operators, so like the divergence and the gradient, that are coherent with the Laplacian that we defined before. And so here, as a sanity check, we show that we recover the behavior of the Hodge decomposition, but in this volumetric setting. Okay, so like it's kind of telling us that we are doing stuff that are not completely random. Okay. But please take the paper for more details regarding that. And so now very quick words about discretization. So since mu and t will involve nonlinear function of Gaussian variables, we use simple quasi-Monte Carlo techniques. Okay, so like we have to do some Monte Carlo to evaluate the coefficient of the differential operators that we define. And then once we have those operators, we do the computation themselves into in a volumetric domain. Okay, and so we choose the simplest discretization, which is standard finite differences. Okay, and we do that in a narrow band. Okay, so like we only do computations where the probability to find the shape is high enough. All right, and so we will end up with, what matters is that we end up with a standard discretization for the Laplacian, which is an inverse mass matrix times a positive semi-definite matrix L. Okay, and we have plenty of numerical study in the paper. All right. And so now the question that matters. How does all of this impact downstream geometry processing applications? Okay. So essentially the key takeaway is that at any point in space where like if the shape uncertainty gets higher, then it will be more and more ignored by the computation. Okay. So like if I take my example from before, that I consider the field mu, which is like essentially the probability to find the shape, and increase the amount of noise that I assume on my input, okay, also like using the model that we defined first. So like, as you can see, at low noise on the left, I have a distribution that is very concentrated around the mean of my shape, okay, so it will like behave very deterministically. But when I increase the amount of noise that I assume on my data, as you can see, mu gets more and more fuzzy, and in particular in the hole, the density like decreases very fast towards zero. Okay, so like the hole is more and more there essentially. And then when we consider, for example, the eigenfunction of the Laplacian that we defined, okay, so like on the leftmost example is the eigenfunction on the mean shape, so like the triangle mesh, and then it's on the volumetric representation that we have above. And so at very low uncertainty, as you can see, the eigenfunctions are essentially the same. And where uncertainty increases, as you can see, this nodal domain is going to evolve to avoid this region of space where like we're not sure that the data is. Okay, so like the behavior of the operators adapt to this uncertainty. Okay, and the same thing goes for geodesic distance. Okay, at low uncertainty we have the same geodesic distance as on the mean shape, but when uncertainty increases, as you can see, the geodesic distance gets slower and slower in this region without data. Okay, and so if you look at the shortest path, it's very interesting to see that above a critical threshold, the shape, like this computation, will tell you it's essentially safer to avoid this region without data. Okay, so like it's a very interesting behavior, I believe. And so we have also other applications in the paper that also validate this insight, right? That you can, like, if you have a standard way to define computation over surfaces, and that you can like phrase it meaningfully with GPIS, or like the tools that we develop show that we like the result gets like adapts to the amount of uncertainty that we have. So it's very interesting. And to conclude, we propose a general framework to extend computation in general and geometry processing in particular to distribution of shapes. Okay, and we do that using the kac-rice formula, and we believe that the kac-rice formula is a fundamental tool to study GPIS. We also show that GPIS are able to encode and interpolate between surfaces and volumes. Okay, at low uncertainty it looks like a surface, at high uncertainty it looks like a volume, where the region without data gets more and more fuzzy. And what's very interesting is that this is quite the same observation that is in rendering. Okay, GPIS are used in rendering, and it's the same thing. They're able to encode between surfaces and volumes, and it's very nice that we can recover this point of view, but from the lens of scientific computing instead of rendering. Okay. And there are some limitations. Of course, it's much more expensive. Like slightly more expensive than doing stuff only on the surface, okay, but of course, like, not the same problem, but it's still reasonable, okay, it's pretty scalable. On most of the examples that I showed here, it's well below 1 minute, okay, and we mostly have no distribution on the output, okay, because like the dream would be to have, if I have a distribution of uncertainty on my input, what's the distribution of uncertainty on the solution of my PDE, but we are precisely working on that, okay, so stay tuned. And then other future work might include treating like other PDEs or geometric tools that might be derived from other geometric functionals. Okay, and so we also acknowledge the support of several sponsors, and thank you very much for your time. Please don't mind asking questions. I'll be very glad to answer. Thank you.